Hey everybody, and welcome to our last tutorial, interference and the two-slit experiment. Before we're gonna start, I want you to see this video here, which is gonna be a really good introduction for us. So cameraman, please zoom into the video. We got it?
The infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands.
In the beginning, God created the heaven and the earth was without a form, and void and darkness was upon the face of the deep. And the Spirit of God moved upon the face of the water. And God said, "Let there be light." And there was a light. And God saw the light, that it was good. People always want to understand what is light. And today we're actually going to dive into it. And two really important people actually really think about what is light, the physical idea of light. So on the right you have Isaac Newton, and Isaac Newton said light are particles. They just hit our eyes, and that's the reason we can see. And many people trust Newton because he have many really good history, right? But then came Huygens, and Huygens said, I think that light is a wave. Remember what is wave? Wave is a disturbance. I have to think about that like breakdance. Wave is a disturbance that moves inside medium, right? So this is a wave, and you say that's light. Light is some disturbance that move in a wave form to our eyes. And we just learned about it in the previous tutorial, right? EMR. And apparently, when you do the two-slit experiment, what are we getting? If you can, please. So I brought the real experiment, the two-slit experiment, and two of the students already measure the distance and the parameters. And something that I want to say that's really important is that he said, "You're going to do the experiment." I said, "No, we're going to do the experiment." Guys, you're inside an engineer faculty, right? In a few months from now, maybe you're going to have a startup. It's time to get dirty. It's time to start to play, and you have the knowledge, especially after Physics 2, which is a really advanced class, right? So if I shoot with the laser, here I have two slits, and you're going to see on the board, if you can zoom in, I see this pattern of waves, right? I see strong places and weak places, and that's going to be our question. So let's go back to the board and try to solve this question. Okay? So here it is. So what I really had there was that. So we were having this kind of thing, and I have here in the middle, here you have two holes, right? And here in the middle I put something really narrow. This is the distance D, and I measure it to be really small. it's 2.3 times 10 to the minus 4 meter. It's really, really small. And I shine that with the laser. This is my laser beam. So you see that I have one source over here of light and another source over here with light. Okay, so if I'm gonna draw this, okay, from top view, I'm looking, this is the laser, this is the screen, right? I'm gonna see this thing. I have here the laser, here is the bottom, and the laser shine upon the two slits, right? You know, it's not on scale, yeah, but this is D. And really far away from the board, from the two slits, I have the board, right? Which is gonna be the screen, right? And you measure the distance. What is the distance L? 2.42. So we can see that this is really small compared to our L. Okay? And this is a key thing in order to solve the two-slit experiment. Great. So the first question I want to ask you, and by the way, this is a red laser. See, this is a red laser, right? And the laser tried to pass the slit. This is the two slits, right? Two slits. Try to pass, but it can only do that through this hole. And the first question I want to ask you, kind of a warm-up, okay, is 1A. 1A is, would omega and K of this laser, which we know its quantities, omega equal 650 nanometer. What is nanometer?
Meters.
Really small. It's 10 to the minus 9. I'm actually doing my PhD at the Nano Science and Technology Institute. I deal with this kind of range, okay? So this is the phenomena of the laser. So remind me, what is omega? Do you remember? I didn't ask you the question. Would omega and K would change when going to this side after passing these two slits? Would omega and K change after the slit? Okay? So remember, what is omega? Do you remember what is it? Omega equal to 2 pi f, right? This is the frequency of the light. And how we can find the frequency of the light if we know that? We have the wave equation. We said speed equal to wavelength multiplied by frequency. So I can plug that in and have 2 pi lambda, right, multiplied by c, the speed of light, right? And this is equal to ck, right? So c not gonna change, right? So let's see what's going on with k. What is k? K is actually, remember, K is the opposite thing to wavelength, right? It's 2 pi over wavelength. Got it? 2 pi over wavelength. So it's like, this tells us how much time play a role in our light beam. Okay, and this tells us how much space play a role in our light beam. Okay, this is the two phenomena. And what I want you to note is, you remember that frequency does not change when you change mediums, right? Only wavelength. Okay, so this is important. So I want you to know that if we would change mediums, for example, here it's L, or vacuum, yeah, and here it's air, nothing would change. But if we're gonna put here something else, for example, water, yes, something gonna drop. Lambda gonna change, and also the velocity would change, right? Okay, so this was just a warm-up. Now let's do the real experiment, okay? So I want to ask you, in some position here, some general position, let's call it P position or point, yes, I want to know what is the electric field. Okay, so I'm going here, camera, yes. So I want to know, okay, what is E at the location P versus time, okay? So what would this be equal to? okay? If we're going to look at the drawing, right? So what's going to happen to the laser? I'm just going to draw it with different colors, but it's the same red color, yes? So the laser would pop up from here and reach there, right? And another beam would reach there and also contribute some electric field. So the solution here should be a superposition of both of them, right? So camera with me. So if this is gonna be the upper one, let's call it R1, and let's call this R2, right? So the solution to that would be E contribution from 2, right, at location P at any time, plus the contribution at location P from slit 1. Slit 1 and slit 2, right? So what is this equal to? We talked about it, that light is what? It's a particle or it's a wave? It's a wave phenomena. Actually, it's more complicated than that, but let's leave it for physics 3, okay? So it has some magnitude, and we know it's changed its value in time. So we have here sinus. We know that the location, it's really relevant to where I am in space. So the beams here and here were equal, but this one go a long range, and this one went a little bit shorter range, right? This point is more close to point P, right? So here we need to put K, but put here R2, this distance, right? Minus omega T, right? Plus the second beam, K R1 minus omega T. Got it? We have these two contributions. So we can join them together and have 2, right? I do some equation for some summation of sinus, right? So we're getting 2 sinus of K R1 plus R2 minus 2 omega T divided by 2 multiplied by cosines of K R2 minus R1. So I'm going to call it delta R. Okay? It's clear?
R2 times R1?
No, minus R1. So I'm going to call it delta R divided by 2. I want you to see something. This is crazy, right? This is changing all the time. We have here the time, right? But this depends only on space, location, right? What is the difference between the beams, okay? So that tells us that there are points, there are locations, right? Locations. There are locations which can be what? Can be all the time 0, if the cosine is 0. Can be maximum all the time, right? So this term is really interesting. There are locations which can be unique, right? Unique. So that's what I really want to do. So, but in order to find that, we need to understand better what is delta R, right? We cannot solve it without understanding what is delta R. This is a really geometry problem, right? So I want you to look at that. I'm going here to the board. So what is actually delta R? If I'm going to take here and put here 90 degrees, you see that this triangle is really like this equal to that. You see it? It's like this is 90 degrees and this is maybe 18.999, right? Something like that. So they are really similar. So I can say that this part until here is approximately R1, right? Why it's true? It's true because of that. L is huge. It's really far away. Got it? And this distance, let's take this triangle out. So this triangle is actually delta R, right? This thing here, right? And what is this? This is the distance between the slit. This is D, right? And another thing, look that each point on space have some angle. What do I mean by that? It's really hard to see, but this is an angle from the center that's going to point P. Yes, I can tell that point P is some, I don't know, let's put it in the middle, y coordinate, right, and tell the location of each point, but I can also use what the camera is actually doing. I can take video 0 angle, and I can open an angle from the camera to me, right? So, for example, 30 degrees, 10 degrees, 0 degrees, right? So we can actually explain everything here using theta, and if we're going to do, if we're going to compare this triangle, the big one, this one, to that triangle, we can see this angle is actually the same theta, okay? If you're going to compare it, okay, think about that. The theta is actually going from here. This is theta. This is 90 degrees, right? This is 90 degrees. This is also 90 degrees, right? And this is the one that completed. So you can actually do the geometry and find that out, okay? So what we understand, the delta R is equal to what? To which kind of theta? Delta R equal to D sinus theta, okay? So you can actually change delta R. So this is our delta R. So section B, yeah, section, sorry, this was C, that was B. What is the electric field at that location? And C was what is delta R, right? And we said that we have this kind of triangle, which this D, this is theta, right? And this is delta R, right? And so that this delta R, according to this triangle, equal to D sinus theta, okay? Good. Now I want to ask you, in which locations, yes?
Sorry, just put there are locations.
Location which can be useful, right? Important, interesting, because this thing is only relevant to space, not time. So in any time, if for example this is 0, I don't care what's happening in time, right? And if I want to see the maximum, only when this is maximum I can gonna see it, right? So which are useful, interesting, unique, okay? Great. So I'm gonna move to that side of the board. So now I want to ask you about these interesting locations, right? So let's do, we are in section D. So where are the maxima? Where on the board we will have maxima? Okay? What location? That's going to happen only when cosine is equal to 1. Exactly. So I'm going to look at the cosinus term. So we're going to have this here. Cosines of k delta R divided by 2. I want you to be what? What is the strongest value that cosinus can have? Exactly 1. And we already know what is delta R, so it's actually we want this to be equal in order to have 1. What we need to have? How cosinus look like? How cosinus? I'm the strongest. So what? This is need to be equal to what?
N pi.
To m pi, right? Okay. KD, okay, good.
The magnitude or just
what?
Is the magnitude equal to 1 or just because the magnitude has to be?
I want all these to be equal to 1.
Okay, so it's 2n pi.
What?
2n pi.
No, it could be also, I don't care about minus and plus. I'm not going to care, it depends on what axis I did, but it's a maximum magnitude to me. Because what is actually minus and plus is the direction, right? Positive or negative of the electric field. So in order to have this maxima value, we need to be some multiplication of pi, right? 0 pi, 1 pi, 2 pi, I don't care, okay? So we want to say that this term, k delta R divided by 2, must be equal to that in order to have a maxima. Good. And we know delta R, let's put it inside. K delta R is d sinus theta, right? And this theta becomes function of what? Of this m, which means we're going to have many theta that's going to give us maximum, right? Divided by 2 m pi, right? Cool. I'm going to that side of the board. Okay, we can clean this concept because I see here pi, and remember what k equal to? 2 pi over lambda, right? So I can write, instead of k, 2 pi over lambda, which we know it's our laser, which is red, right? 2 pi over lambda, d sinus this special theta, which is a function of the specific m we choose, right? We have here 2 equal to m pi. So forget about your radius, I don't need you. Forget about you 2, I don't need you. And we're going to have sinus theta equal to what? To m multiplied by lambda divided by d. You see it? Okay? And let's say that you don't want to talk in theta, you want to talk in y, as we have here. You see this y? Okay? So the shift is really easy. Why the shift is really easy? Because the angles are really, really, really small, right? So if you're going to think about it, you see this is our triangle. Sorry. This is, let's go here. Okay? I'm going to clean it. Okay? So I want you to see this is theta, right? This is L. This is, for example, y maxima, right? Let's do really small m. Y maxima, right? Cool. So if we want to know that, what is this angle equal to? This angle, this divided by that, sinus theta is that divided by that, ym divided by L, right? Let's do it even easier. Okay, I write here x. Sorry. Let me make it with the same notation. Oh, this is really bad. No! What have I done? Okay, so this is L, and here I want to put x. Sorry for that, xm. Okay, so xm. This is x, and this, for example, is xm because we're talking about a maxima. So if we're going to take the tangents, okay, I can't look at this. If we're going to take the tangents, okay, tangents of theta m, it's equal to xm divided by L. But I want you to remember that what is tangents actually? Definition is sinus theta m divided by cosines theta m, right? And if we're talking about really small angles, which is the case because L is much larger than D, okay? So that's going to result in a really small angles, okay? So this is actually, cosinus is going to be equal to approximately 1. So tangents is actually kind of a sinus. You see it? It's really approximate to a sinus, so I can take this term and actually put this inside. And then we're going to have that xm equal to, I'm going to multiply by L, m multiplied by L, lambda d. Right? Let's calculate that. We know that, right? What that equal to? What is lambda? It's 650 nanometer, and D, I think I just cleaned it from the board, but we know it also. Is someone calculate this for us? Startup people, this is your time. L is 2.42 meters. I hope this is correct. Okay. Let's see if the physics works. Yeah. Fast, come on. Okay, I'm gonna make a cameraman. In the meantime, cameraman. Okay, so this is the experiment. We have here the laser, we have here the 2 slits. I'm gonna open the laser, and I'm gonna join us and check the results. Okay, so take this and tell me where is the first maxima. Okay? Yeah, come and measure it. What is the result?
0.0068.
0.0068. Okay, meter. This is really, really small. Zero. Are you sure?
I mean, the nanometers I turned into meters.
This is 10 to the minus 9.
Yeah.
This is 10 to the minus 4, and this is 2.42. Right? Okay. So come here. No. I want you to measure. What is the distance? Don't look back because it's a laser. It's going to kill you. Okay. Wait. Here it is. Where is the brightest point? Wait. Here. Wait a second. Don't look back. Otherwise you're going to die. Okay. I want it to be bright as I can. Okay, so if the camera can do zoom with me, it's going to be perfect. So wait a second. So this point here in the middle, it's the strongest point, right? And this should be the distance between two maxima. This is 0 and this is 1. Okay, so what is the distance between the middles?
Like it's super small.
It's super small. Let's do some. This is not the brightest. This is the brightest. Yeah, it's few. I don't know. I think it's really small, right?
Really small,
it's really small. It's kind of a half of millimeter, something like that. It's really tight together. So that's what we get, right? So, but don't forget we have this M in front of it. So the first maxima are going to be exactly at 0, right? And then we're going to have 1. And then we're going to have 2. What I should have been done, I should put this two-slit experiment really far away. And that would increase that. Then we're going to add a more reasonable value that you can approximate, right? So, but that was the intention. Okay? Good. I close the laser. Good. Okay. So the same concept can be done in order to analyze what are the minima, right? Where's the location of completely darkness? Okay, when the wave actually gonna meet each other, not high point to a high point, right? This is the wave. So right now they are the same. This is a maxima. This sum up with that, so it's gonna increase. But if this is on minima, right, and this is on maxima, they're gonna sum up to be 0. So there's locations where there's darkness all the time, right? And also it's important to say that these maxima points actually also sometimes 0, but you can't see it because the frequency is too fast. You cannot note that it's actually sometime dark, okay? But there's location that's going to be always dark, okay? Let's find them. So we're going back to here, right? Right now, what we want to ask?
0.
Now, if we are in section not D, but F, so this is going to be A, B, C, D, E, sorry. E, yeah, E. So right now we want to know minima, right? So this should not be 1, should be all the time 0, right? And that's happened where? This is a little bit more complicated to understand, right? Look at it. This is cosines, right? So where the first place it's 0? Pi over 2, and then 3 pi over 2. Oh, and then boom. And it's continued that way. So we're gonna have. Sorry, this is. I'm gonna help you to find out. This is 1 multiplied by pi. Okay, think about that way. So this is 5 pi over 2. So where the location? What this need to be equal to? To pi over 2. We see it all the time. But what we have in front? Odd number. We need odd number. How we can make an odd number in a mathematical way? Great, we know how to do even. We're going to multiply by 2 and then we're going to fuck them up, do -1, right? So if this, and I do note a little m because we are talking about minima, -1, okay? So that's what we want to have here. And this is equal to the argument, to that. So k we already talked about, it's 2 pi over lambda. Delta r is d sinus theta minima, right? Divided by 2. You die with that. You die with that, and we're gonna get that sinus theta minima, right, equal to what? To 2m, sorry, I did here plus 1, not minus 1, okay? Plus 1, lambda divided by 2d. And what do I need to do in order to have it in meters? Like at x coordinate, not theta? I can shift this sinus theta to, this can be shifted to xm divided by L. So it's just to multiply that by L, right? Clear? I'm gonna draw it here. So if I want to have a minima, x of a minima, it's equal to just multiply by L the term that we have. 2m plus 1 multiplied by lambda divided by 2d. And we can also calculate that. I want you to see, just to see on the board, where's the laser? Cameraman, I'm trusting you that you can catch the beam. Wait. Okay, so can you zoom in really hard? Do you see there's location of completely darkness between the dots? Completely darkness, okay? So these are the location. Where are this location? You can put here m equal 0, 1, 2, 3, and you can do it positive and also negative, right? In this manner, this is the middle, so you have nothing to the right and nothing to the left. And then after that you have maxima, so you can jump between them to the left and to the right, okay?
It doesn't matter if it's 2m plus 1 or minus 1.
It's a definition. So the common thing to do is plus 1. Okay? Yes?
Don't use the green marker.
What?
Don't use the green marker.
Don't use the green marker. So you missed that?
No,
okay. Okay, so in general, this is a really important formula for the exam. Okay? This one and the maxima one. And now I want to show you another concept and bring us back to the beginning of the class. Okay? Let's go to this side of the board. Okay? So at this experiment we had only air, right? And air, it's not gonna affect that much. Not gonna affect that much on the situation, because air is actually behaving a little really similar to vacuum. Yeah? But if there was a little bit rain, right? And this point here next to the slits, here's the slit separation. So one of the opening of the slit actually have a raindrop, okay? In some length, let's say small l, okay? Little l, okay? So now things gonna change. The picture is not symmetry to that side and that side. There's no symmetry, right? So what's gonna happen in this side, in this case, right? So what I want you to understand is that what's happened. So we have the wave, right? This is lambda, right? It's moving at the speed of light. And then when it's entering different medium, for example, the raindrop, yes, H2O, something happened to the wavelength. The speed decrease. Right? And for the light, it's really easy to move in vacuum and in also air. There's nothing to bump into, right? The atoms really far away. But in water, they are really dense. Okay? So what actually happened is that, here let's write it, C equal to lambda F. Right? That's what's happening outside. But inside, V equal to lambda F. Okay? Would F change if we're going to change medium? No, the tempo of the light gonna be the same, okay? If I'm gonna give some, I don't know, slaps to something, it's gonna feel the same slaps in the same frequency, right? But something gonna drop, and this is actually the speed and the wavelength, okay? The wavelength gonna decrease and look like that. You see that it's more dense, and then it's gonna go back to be really wide as it was before. Okay, so what's gonna happen is actually that the wavelength gonna shrink by that amount, the original one divided by n. N is the refractive index. It's a material dependence phenomena, okay? Let's give you a few examples. For example, this is N, this is gonna be material, some material. I'm gonna change to the black one, here it is. So for a nothing vacuum, what is N equal to? Remember? It's equal to 1, okay? N actually always gonna be bigger than 1. And if you're gonna use air, so it's not gonna be 1, it's gonna be something close to 1, I think it's 1/3, I'm not sure about that, but it's something really close to 1. So most of the time we're gonna say it's wrong, 1, give us a break, right? But what happened when we go into water? Now it's not negligible at all, right? It's 1.3, right? 30% more. And if you're going to go to glass, okay, in many experiments and startups that you're going to have, you're going to use laser measurements, and you're going to have water in glass because it's easy to see through them, right? This is already 1.5. This is not a joke, okay? So this changed the game for the light. You see it? Okay. So what's actually happened here is, you see that this is the new lambda, and we also have the new speed. What is the new speed? Multiplied by f equal to lambda f divided by n. So you can say that the new speed is actually Vn equal to c divided by n. You see what's happened? Okay, so this is the concept. Great. Now I want us to fill some table, not this one, a new one. I'm going to go here. So a new table, and I want you to notice between two different lengths that you can observe. Okay?
I have a question.
Yes, go ahead.
What is n?
N is the refractive index. If you're going to have light, you know that light propagates in the speed of light, which is really fast. 3 multiplied by 10 to the power of 8 meters per second approximately. But if you're going to let the light, the same beam of light, go through oil, through glass, through water, you're going to see that the speed decreases. The speed is less. How much less? You can do the experiment and measure. Okay? There's a famous experiment on YouTube when somebody shine light through a bottle of cola, I think. And you see the light propagate before and then after, okay? And you see that it's really taking the time inside the water, okay? Cola is basically, most of it water, right? So you can do that, and you can understand how does the wave look like in space. This is lambda. So lambda have the same thing, because it's a linear equation. If you divide one, you need to divide the other term of the equation, right? So, but I want you to notice there's two paths that the light go, okay? First of all is the geometry path, okay? Let's do that. I want us to do that, okay? Complete the table, okay? So there is a geometry path, okay, that the light could go. And we're gonna denote it by xg, okay, geometry one. And this is what we see through our eyes, okay? This is, if I'm gonna take a ruler, put on the experiment, and I'm gonna measure it, okay? So this is gonna be, let's give names to each location, right? So we have this point, and this point, and this 90 degrees, right? So this gonna be called F, this location. This already have P, that's gonna be E, this location here, and that location where the second slit is, we're gonna call it C, right? So the first beam, this is a first slit, right? Have the distance R1, which is equal to EP. This is the distance, right? And here, actually I should do it more like that, give it more room. EP R1, and here R2 equal to what? So first of all I need to go L, right? I need to go through L. And then I need to go delta R, right? Remember the triangle? This is delta R, we said. So L, it's not all delta R. Let's do it smaller. It's really small. This is L. Okay, this is L, and this is delta R. And then I need to go through delta R minus L, right? A smaller distance. This whole thing was delta R, right? And then I need to go through FP. But remember what we said that FP is? FP equal approximately to, look here, FP approximately equal to EP, right? So this is approximately EP, okay? So this is the different distances that this is two light beam goes. And now I want to talk about the optic way, optic path. What is optic path? We don't see the optic path, but the light see not the geometry path, but the optic path, okay? When the light go through this slit, the upper one, right, R1, you go to it and we need to multiply it by N. N multiplied by EP, and in our case, this is equal to only 1, right? Because it's L or vacuum, it's the same thing, right? It's really close, okay? But here, it's more complicated, right? L multiplied by N of H2O, of water. You see it? So this increase our path. That's what's going to happen. You see it? Because the light going to spend more distance, yeah, kind of a distance, more lambda, more time periods inside the water, because the wavelength becomes shorter, right? So here we're going to need to multiply it by N, right? And here plus the rest, right? Which is delta R minus L plus EP, right? And this is going to be multiplied by 1, right? I'm going to go here. I'm going to explain everything here. So what's going on when we talked about the geometry and the optic? So the geometry was to measure what is each part and sum it up. This is the distance, the geometry distance. But the optic one take into account which material I'm going through. Each distance that I'm going to multiply it by the refractive index. The refractive index of EP is 1. There's no material, it's only air. White, right? N2, O2, right? Air. Yes? But when we go through the water, it's actually H2O. And the small part which is L. And this is going to change dramatically the picture, okay? Why so? Because remember what was delta R before? Delta R was actually this minus this, right? And if you're going to do that, right? Sorry, this minus this. So we're going to have L plus delta R minus L plus EP, right? Minus EP. Right, so this cancel, this is delta RG geometry. This cancel, yeah, makes sense, right? It's the same thing. But right now, delta R optic is different, right? Because we have this thing here. So maybe this cancel up, right? Ln, right? Ln plus delta R minus L plus EP minus EP. So this dying out, right? But I have this term, which is L, I can put L inside, N minus 1 plus delta R. So we have this extension. You see it? So this is a classic thing for the exam, right? So you're going to have the normal thing that we did in class, the two-slit experiment, but then something going to show up, right? A glass, a water, another gas, and then you need to be careful about it, okay? So let's right now find where is the new, what is the new electric field, okay? So it's the same, right? It's the same thing. It's E PT, right, equal to the summation of the two sinus, right? We have 2E sinus what we have before, right? But here in the cosines, Remember that we have K delta R divided by 2? Now the geometric path and the optic path are not the same. We should put here optic, because light care only about the optic light. Okay, the optic path. So this term actually improved to this cosines, right, of K, and now we have here L n minus 1, right? L n minus 1 plus delta R geometry, right, the original one, divided by 2. And if you, for example, want to find maxima, okay, so this need to be equal to 1, right? Which means all these need to be equal to 1. Understood? You see what's happened here? So the picture is not symmetry anymore. This delta R is actually shifted to this term, which is n is the refractive index, right? And now this need to be equal to 1, which means that this equal to K L n minus 1. K is 2 pi divided by lambda. Okay. If we compare everything, we're going to have that sinus theta m. Wait a second. What is the time? 3:24. Okay, so we're going to finish. Okay, so look. So we have this term and we want it to be equal to 1. So this term have to be equal to m multiplied by pi. Clear? We want maxima. So if you're going to ask for that, and we know what is delta RG, right? It's this sinus theta m, dependent on that. K is 2 pi divided by lambda of the laser, right? The original beam. And we're going to get sinus theta m equal lambda m plus L 1 minus n. This was not here before, right? Divided by d. Okay, and if we want to move to xm, it just means to multiply everything by L, right? So L lambda m plus L 1 minus divided by d. Clear? You see what's happened? And now I can ask interesting question. Okay? The m equal to 0 gonna be above my axis in the positive or below my axis? What's gonna be the value of the first 0? So we're gonna do it here. So question I can ask. So what is the sign of xm0, right? The strongest maxima, right? 0, 1. Okay? So you just gonna take that equal to 0. L d, and we are lucky this is just 0, plus L1 minus n. So it's L divided by d multiplied by 1 minus n. And this is equal to what? This is a positive number always, right? Just length, right? N is always larger than 1. So this is actually a negative. So the strongest maxima gonna be below. So right now, before we're gonna finish, I want to show you a quick video, okay? And with that, we're gonna end the class.
So, when we throw things, that is matter, through 2 slits, we get this, 2 bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through 1 slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through 2 slits, we should get, like the marbles, 2 bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched.
So guys, we finished the class of Physics 2. We finished the class of Physics 2. It was a pleasure to me to teach you, and there's a lot of mysteries in Physics 3 that's facing you ahead. So wish you the best luck in the exam, and we're gonna do a practice for the exam next week. See you next time.